Quiz 18.2 explores the relationship between Gibbs energy and temperature. We have two questions that are essentially the same, just a little extra practice. So the first question says to consider this reaction and find delta H naught and delta S naught for this reaction. We'll be relying on Appendix 2, where we have all of those tabulated thermodynamic values. So here's our reaction: CO gas plus H2O gas. And this is actually an equilibrium reaction, and that's going to produce H2 gas plus CO2 gas. And I like to, just to make these sorts of problems easy to organize all the data, I like to write the delta H naught of formations for everything on the top. That'll be in units of kilojoules per mole. And so I go through Appendix A2 and I find that I have negative 110.5 kilojoules per mole for carbon monoxide, negative 241.8 kilojoules per mole as the enthalpy of formation for water, 0 for hydrogen because it's already in its elemental form, and then negative 393.5 kilojoules per mole. And then on the bottom here, right, the standard molar entropies, and this will be in joules per mole Kelvin. You'll notice it's not an entropy of formation. Entropies we can measure against an absolute zero standard, and so we don't need to look at formation reactions. This is the standard molar entropy, and this will be 197.7 joules per mole Kelvin, 188.8 joules per mole Kelvin. Hydrogen will have a standard molar entropy, 130.7 joules per mole Kelvin, and 213.8 joules per mole Kelvin. Okay, and so to calculate the delta, and I'll just say delta X of reaction, okay, because it's the same formula whether it's enthalpy or entropy. You're going to take the sum over the products, the stoichiometric coefficients times the X values for each of your products, minus the sum over reactants, the stoichiometric coefficients times their entropy or enthalpy values from the table. And let's just put that into practice here for this reaction. This would be CO2 plus hydrogen minus carbon monoxide minus water. So for enthalpy, I would take negative 393.5 plus 241.8 plus 110.5. For the entropy, I would take 130.7 plus 213.8 minus 197.7 minus 188.8. And in the end, we get delta H naught of reaction equal to negative 41.2 kilojoules per mole, and we get delta S naught of reaction equal to negative 42.0 joules per mole Kelvin. And we'll go ahead and convert this into kilojoules per mole Kelvin so that the units match with everything else. Just divide it by 1,000. Kilojoules per mole Kelvin, 0.04 2 now. So that's delta H and delta S. Now find Gibbs energy at temperature of 315 Kelvin. We know that delta G is equal to delta H naught minus T delta S naught. And so we'll just plug those values in. That's a negative 41.2 kilojoules per mole minus 315 Kelvin times a negative 0.0420 kilojoules per mole Kelvin. And this is going to give us a delta G naught at 315 Kelvin of negative 28.0 kilojoules per mole. And then the last question is, under what conditions is this reaction going to be spontaneous? Let's go ahead and erase the top. We don't need this anymore. The threshold will happen when delta G is equal to 0. So 0 is equal to delta H naught minus T delta S naught. And that implies that T is equal to delta H naught over delta S naught. We'll just plug in those values. Where are we? Negative 41.2 kilojoules per mole divided by 0.0420 kilojoules per mole Kelvin, and we get a threshold temperature of 981 Kelvin. Now, is it going to be spontaneous above that threshold or below that threshold? Well, we've got an exothermic reaction with a negative delta S, so this is going to be spontaneous below that threshold temperature. Okay, and now we'll just kind of do the same thing with a different reaction. So we have 2 NH3 gas in equilibrium with N2 gas plus 3H2 gas. And again, we'll do the delta H naught of formations on the top and the standard molar entropies on the bottom, looking up all of our values from table, from Appendix A2. And we're going to have negative 45.9 kilojoules per mole. And then these are both a 0. Makes that easy. And then here we have 192.8 joules per mole Kelvin, 191.6 joules per mole Kelvin, and 130.7 joules per mole Kelvin. And so X in this case, we do have some coefficients. So we would take X of nitrogen plus 3 times X of hydrogen minus 2 times X of ammonia. In other words, for the enthalpy of reaction, we would take 0 plus 3 times 0 minus 2 times negative 49.5. And that gives us a delta H of reaction equal to a positive 91.8 kilojoules per mole. And for the delta S naught of reaction, we would take 191.6 plus 3 times 130.7 minus 2 times 192.8. And that equals where am I? That equals 198 joules per mole Kelvin. And we can go ahead and divide that by 1,000, 0.198 kilojoules per mole Kelvin, just like so. Okay, so we've got our values for delta H naught and delta S naught. Now find delta G naught at 550 Kelvin, so delta G naught is going to equal delta H naught, 91.8 kilojoules per mole, minus 550 Kelvin times 0.198 kilojoules per mole Kelvin. And that's going to equal negative 17.1 kilojoules per mole. And then let's find the conditions where it will be spontaneous. Well, I know that my temperature threshold is going to be delta H over delta S. 91.8 kilojoules per mole over 0.198 kilojoules per mole Kelvin. You can't quite see that, so let me just get rid of that. Okay. And that is going to equal 464 Kelvin. Right? And then when will it be spontaneous? Above or below that? Well, we have a delta H, which is endothermic. That means at 0 Kelvin this is non-spontaneous. And then a positive value of delta S of reaction will make it more spontaneous at higher temperatures. So more than 464 Kelvin or above 464 Kelvin is when this particular reaction will be thermodynamically spontaneous.